Good morning, everybody. This is Cameron Brett. We're just going to give just another 30 seconds or so to allow some people a little bit more time to jump on. So we'll start very, very shortly. Thank you. For those who are just joining, we're just going to give a few more seconds to allow people to join. Okay, I think we'll go ahead and get started now. Okay. Hello, my name is Cameron Brett. I'm president of the SCSI Trade Association, and I'll be hosting our webinar today. Of course, just hope everybody is staying safe and healthy during these unprecedented times. And the webinar is something to help break up your day. Today's webinar is on 24 gig SAS and how to test it. Joining me today is Mike Micheletti from Teledyne LaCroix, who will enlighten us on how this is done. A couple of quick housekeeping items. The webinar is scheduled for 45 minutes today, and we expect about 35 minutes of presentation time, and with the remaining time available for questions. If you do have questions, please submit them via the chat box at any time, and we'll tackle as many of them as we can in our allotted time. If we don't get to your question on the webinar, we will certainly answer it by email. And the last housekeeping item is that all the slides that are being presented today are available for download in the attachments and links section. Here's a quick look at the agenda for today. This is certainly more on the technical side than some of the other webinars that we've done in the past. Mike Micheletti will dig into the details on how to test specific features in 24 gig SAS. And just a quick heads up that you'll see the term 24 gig SAS, and that is a marketing term. And you'll see SAS-4 used in Mike's portion, and that is the proper name for the specification. And also just a quick heads up that we are planning for a 24 gig SAS Plugfest at the University of New Hampshire's Interoperability Lab, planning for this summer. Stay tuned for more details. Just a quick backgrounder on the SCSI Trade Association. It's an organization that was formed over 20 years ago by companies that developed and sold products built around the SCSI command set, which we commonly call SAS today. It is the marketing arm of the ANSI T10 Technical Committee that is responsible for developing technical specifications for SAS. The SCSI Trade Association markets and promotes the use of SAS in data centers. And we welcome additional companies to become members of the STAY and contribute to the evolving use of SAS. Okay, here's a market research chart that we tend to show and update periodically. And really, the message here is that SAS is a very, very prominent storage interface, and it remains so today and in the foreseeable future. SAS and SCSI has been around for decades, and according to this recent IDC report from December 2019, SAS connectivity is going to be around for a long time, well into 2023 and beyond. But between hard drives and SSDs, SAS connected storage continues to grow, and unit shipments remain strong going into 2023. So this is a very good time for 24 gig SAS designs to take foothold here. And this slide, just a quick overview on some of the highlights of 24 gig SAS. These are some of the changes that have been made from 12 gig SAS to 24 gig. In particular, in the physical layer as well as the protocol block level. The physical layer enhancements include doubling the effective bandwidth from 12 gig with improved encoding and adding 20-bit forward error correction, also called FEC. With the physical layer enhancements, they deliver higher IOPS and bandwidth performance, as well as improved reliability. Over on the right side, on the protocol and block portion, the fairness updates help to improve performance across multiple generations of attached devices, typically in larger topologies. This includes SAS and SATA, as well as hard drives and SSDs in the same deployment. Storage Intelligent enables more efficient streaming and data management to SSDs, and this translates into improved SSD performance, SSD efficiency, and quality of storage performance throughout the whole topology. Lastly, SMP priorities also help to improve prioritization of configuration and effective management communications. And now I'd like to turn it over to Mike Micheletti, who will enlighten us on testing of 24 gig SAS. Mike, the floor is yours.
All right. Thanks, Cam. And thanks to everyone for logging in today. Hopefully, Teledyne LaCroix is familiar to most of you. We develop test equipment for serial data testing applications, and my group does the protocol analyzers. So these are primarily for R&D testing, used in the lab setting, right? Chip vendors, system vendors, they both use our equipment to verify devices are, well, following the protocol, really. So we're always on the bleeding edge of these new technologies, like 24 gig SAS. The presentation I've got here is designed to give you a concise summary of the changes in SAS 4. Along the way, I'll try to provide some tips on testing these new features. The material assumes you have some familiarity with SAS protocol, because we're going to focus on the new stuff. Starting with the Gen 5 signaling rate. As I'm sure most of you are all aware, they use 22.5 gigabaud signaling at the physical layer, combined with more efficient encoding to effectively double throughput rather than just doubling the 12 gig frequency. Really, the biggest changes are down at the link layer with the introduction of packet mode encoding. Our analyzer is really the only way you can actually see what's going on there. SAS 4 does utilize FEC to protect data integrity. That's a significant change. Another improvement, APTA. They basically created a protocol for doing transmitter training on the fly without resetting the link. We'll touch on that. And then persistent connections. One of the new ways they're trying to reduce overhead in SAS 4. Okay. We'll start with the basics. I'll go through this quickly because we have a lot to cover. As I mentioned, the biggest change in SAS 4 is at the lower layers, the logical D-word formatting. In the 12 gig world, packet structures are D-word aligned. And in the 24 gig world, protocol traffic is aligned around 4 D-word frame segments. On the wire, it's really going to look pretty much the same. This is a test unit ready command viewed in our link tracker with the 24 gig traffic on the right. But you can roughly make out these new 4 D-word SPL structures because of the 2-bit SPL header at the beginning there. So that header is used to distinguish between segments that contain primitives or data. And I found the term packet mode in SAS 4 a little confusing. It really doesn't correlate to an SSP frame at all. It's really just a chunk of data. It takes multiple SPL chunks sent sequentially to make a logical SAS frame. And, looking closer at the basic layout of an SPL packet, again, there's that 2-bit packet header, 128 bits of payload, so 4 D words in each segment, and then 20 bits of FEC. Every SPL packet is fixed in length, 150 bits, In the spec, they show the 20-bit pattern at the end, but it's really interlaced on the wire within the payload, always in the same relative position. These are the three basic types of SPL frame segments. The 0, 0, and 1, 1 headers are always scrambled idle. 0, 1 is the header for the primitive segment type. You may notice that there are several new primitive types, and I'll cover some of these. And then the 1, 0. That header is used to identify your logical SSP, SMP, STP segments. So your SAS data traffic is always 1, 0. SPL packets are sent sequentially, back to back, always, going in both directions, and there's basically always going to be an SPL packet on the wire, even though it may just be scrambled idle. Now, it's the responsibility of the PHY on the receive side to verify the FEC and strip out those bits from the packet. It passes the 128-bit pattern up to the higher layers, which reassembles them into logical SAS traffic. So that's how we yield 128 bits. Again, they could be primitives or logical data traffic. Main point here is that these packet mode structures, even with the FEC bits, still have lower overhead than SAS3. So AP10B has 20% overhead, reduced to 17% in SAS4. This graphic is right out of the spec, and I found this to be pretty helpful in understanding how the different packet types will appear on the wire in SAS4. It defines 6 different SPL packets. The data and the standard primitive segments are the items you're probably familiar with, but they now have 3 new binary primitive types. They mostly came up with these as a way to send more information inside a primitive for specific situations that can occur in 24 gig. Again, your logical SSP frame segment is going to have 1, 0 as the header, and then after stripping out the FEC, you're left with the 4 scrambled D words that will be part of a SSP, STP, or SMP frame. Data frames are always scrambled for EMI. Now, in our analyzer software, we have the frame inspector, which is our lowest level view of the packet mode traffic. It lets you drill down on the raw data for an individual frame, and I'll be highlighting this view a lot because it's the only way to actually see packets in this SPL format. This image shows segments that contain SSP data, each segment on a separate line. There's a packet header on the left there, and we don't show the FEC bits in this view. We're just looking at the 4 D words, 128 bits, hex format, always shown unscrambled. So this is what gets passed up to the link layer. The other critical SPL packet is the primitive type. Most primitives here have the same role as they did in SAS3. They're used for acknowledgement, flow control, opening connections. But now they can appear bundled together in an SPL primitive segment, usually in groups of 4, but not always. The link layer can send primitive, idle in a single segment. Primitives are still always sent unscrambled, never mixed with data. You never see parts of a SSP data payload inside one of these primitive segments. One of the more confusing points, they elected to encode legacy primitives using 10-bit symbols, not to be confused with AP10B encoding, just 10-bit patterns. So this table maps out the character placement for just one of the 4 primitives in a segment. So still 32 bits to transmit a primitive. They don't use the K28.5 symbol as the first character now. Instead of your normal comma character, they use just 2 bits, which they refer to as a reduced control character. they take the remaining 3 bytes of that primitive and convert them to 10-bit patterns and place them in the second, third, and fourth position. So still 32 bits total. They do this for all 4 primitives in the segment. So 4 times 32, 128 bits total. They add the header to make 130 bits. Only then do they do the FEC calculation, which yields 20 additional bits that are distributed throughout the payload in these other positions. But we'll come back to the FEC in a second. So still looking at normal primitives, but in our frame inspector, this is something you'll notice only when you go down to the lowest level. When you see 00 in this position, it stands for K28.5. 11 represents K28.3. So that indicates a SATA primitive. So they're representing these control characters now with just 2 bits instead of 8 bits. In our frame inspector, there are 2 important columns here. The description on the left gives the decoded primitive name, and the payload column on the right is how we show the raw data for each primitive. So just to clarify this, we actually display the primitive parameter select in binary. So when you see 0 in parentheses here, we're showing you binary. Then the next 3 bytes are shown as 10-bit symbols. So the receiver for a packet mode 5 would decode this first primitive here as an open accept, because what he sees is the SAS control character K28.5, and then 10-bit symbols shown sequentially, and those are going to, of course, be recognized at the link layer as 3 of your D16.7s. Okay, so for a complete picture, we should also quickly review a typical SSP frame. This is a write 10 in this first column. We decode the field names for each segment. Then next to that is the payload, right, which we show in the raw 128-bit format. Each SPL segment is going to be on a separate line, right? So you can see how we decode everything here. This is the start of frame. It's a primitive. You can't mix primitives and data, so it's by itself. They'll use a line or idle to fill up any extra space. Then you have your data payload. We're actually showing these as individual D words. Just like with the primitives, the data SPL segments won't always fit perfectly in the 128-bit format, so you would send scrambled zeros to pad the last positions in that SPL. And finally, there's binary end of frame primitive. And the number 2 here actually reflects the 2 padded D words after that CRC. Okay. Got a little off track there with my clicks. Hold on one sec. Okay, sorry about that. I've got one more section here. Okay. I guess there's a little bit of latency on my clicking, and so I will get caught back up here. Okay. Okay, so now, yeah, we went through the starter frame. and the D word. Okay. Now, if you're looking at the data segments where we have the SSP D words, these basically are shown in hex, where what I've highlighted here, the D words. But we're showing the, why this is jumping the wrong direction in some cases here. All right, so yeah, basically this is, a little bit of a confusing point, which I'm trying to clarify with a bunch of pointers, but apologize for the clicking. Again, primitives are the point here is that the primitives are going to be shown in full binary, and data segments are going to be shown in hex plus 5-bit codes. And we did this because basically this is how the spec shows it. All right, so we looked, at the basic low-level packet mode traffic. What about the link training? That's always, one of the first challenges when you're testing new devices. Will they link up at 24 gig? So let's go through that. Here is the SAS speed negotiation diagram that we all know and love. There's not a lot of difference between 12 gig and 24 gig speed negotiation. To get to the higher speeds, all the SNWs will start with RCDT. That's the rate change delay time. It's a quiescent period where you're supposed to send OOB idle for 500 microseconds. Both PHYs will typically go through SNW1 at 1.5 gig. You would see them transition from a line 0 to a line 1, indicating the point where the PHYs have reached D-word synchronization for that SNW. They move to SNW2, does the same thing at 3 gig. If either side's going to fail to lock here, they would continue with the align 0 for the duration of the SNW time. If it's a 12 gig or 24 gig capable link, it has to support the SNW3, where you would do the PHY capability exchange. Okay, and again, here you would wait 500 microseconds. You're still supposed to send the OOB idle during that RCDT time. Then you'll send the COM wakes. Again, those are expected to be sent from both PHYs, assuming they support SNW3. So assuming they are 24 gig. The PHY capability message still uses the same format as SAS3. Obviously, Gen 5 signaling is now defined, right? But we're still using COM wake signals to transmit PHY caps. Now, your protocol analyzer should, of course, allow you to capture this exchange, and this is what it looks like in our software. The quickest way to find the PHY capabilities in a trace is to go to the quick search menu. You would just start typing SAS, and then you'll see the reset event. If you don't see it, that means it wasn't captured in the trace. But that will take you to the SNW3 stage. This is our field view that shows the fully decoded capability bits. So to get to the Gen 5 rate, both sides would need to report Gen 5 capable. If there's any kind of mismatch here, they're supposed to pick the next highest commonly supported speed and then move to the next stage. For packet mode devices, the 24 gig link training is only slightly different than 12 gig D-word mode. They still use the pattern marker to signal the start of a training pattern. It's still 20 UI high, then transitioning to 20 UI low. Each PHY will consider transitions with 38 to 42 to be a valid marker. So there's some built-in slop there. Immediately following the marker, the TTIU packets are sent. For the TTIUs themselves, SAS4 uses the same basic approach as they did with 12 gig. No change to the message format, still using D-word size structures, 32 bits total, separate control word where each site can make a coefficient request. The status word always reflects the status of the file that sent it. So for example, 01 here means, hey, that update you requested is complete. So after the TTIU is sent, a SAS4 device will send 59 SPL segments, which contain scrambled idle. So that's 59 128-bit SPL segments, where SAS3 would just send 58 D words of scrambled idle. So with 24 gig, the scrambled idle stage is longer. And then they use a new primitive, ntrain. This is one of those extended binary primitives. So that's used to delineate the end of the pattern now, and really the start of the next stage. So this basic training pattern repeats while each PHY tries to improve the signal integrity of the channel. Just like with 12 gig training, both sides need to signal that they have completed the TX training window by asserting the train complete bit, and then they can move on to the last stage. Now, if either side fails to reach that stage, they're supposed to keep sending the training sequence. If they can't get to train complete within 500 milliseconds, it's considered a failed S&W, and they're supposed to fall back to the next lower speed. Okay, assuming devices complete TX training, they move to receiver training, the train RX S&W, and this is, of course, right out of the spec. This image from the spec, again, shows just one direction. But, of course, you know, this sequence is going on in both directions. And this stage is required in SAS4. You have to participate in receiver training. Only difference here is that where 12 gig use the train done primitive, in 24 gig they'll use packet sync lost. This is one of the new extended binary primitives, which I didn't really cover. I have a longer version of this presentation on the Teledyne LaCroix website. So if you want some of the nitty-gritty details on binary primitives, you know, go to our website, search for webinars on demand. Again, there's a longer version of this material there. Anyway, both sides start by sending packet sync lost. They're basically using this as the training pattern now. Okay. At some point, the PHY gets D-word synchronization. Then he can switch to sending packet sync. He has to continue sending packet sync until he receives a packet sync from the other side. This also resets the scrambler, okay? So how do devices actually do all this equalization stuff? That's all considered vendor proprietary, and it's not defined in the spec. The only requirement here is that he must send at least 4 packet syncs and then receive at least 1 in order to move on. So send 4, receive 1 before that MRTT expires, which is 20 milliseconds. So in this illustration, he's sending packet sync, then he finally receives a packet sync from the other side. Only here can he be certain that the far end has reached D-word synchronization. So then the link layer should start sending SPL traffic. If no packet sync is detected within MRTT, that would be a training failure, and they would, again, fall back to that next highest speed. So that's basically how the receive training side has changed in SAS 24. Okay, just a few more key changes. FEC is new in SAS 4. The PHY committee determined that using FEC was really the only way to get to the 10 to the minus 15 on the bit error rate. So they add 20 bits of FEC to every SPL segment. which can now correct up to 2 bad symbols anywhere in the packet. So this provides added margin for loss in the channel. The FEC calculation starts with the 130-bit SPL packet and payload, and this is after scrambling in the case of data, right? This is used to generate 4 5-bit parity symbols. These are the FEC bits. They're, of course, not scrambled, but they're interleaved across the SPL segment, which, helps provide even better protection for burst errors by chopping it up. And then the RSpec calculations are actually, it's really more than we can get into here. It's pretty complicated. So I'll just touch on, the test implications. How do we test FEC? The easiest way is to use the jammer, which sits in the line and can randomly add FEC errors to live traffic. You could also create these kind of bit flip errors with our exerciser, but it's much easier to use the jammer. It lets you select events from a pull-down menu, and you could pick an SSP frame or really any primitive like the N train here. You would then select which type of error you want to inject, as shown. You have the ability to insert a correctable or an uncorrectable FEC error. So this lets you force an error to basically see how the target handles it, and also, any recovery that could happen at the system level. So how does the analyzer show correctable FEC errors? The key thing here is the analyzer is capturing this bit stream, errors and all. So if there's a bit flip, the analyzer will, use its own algorithms to perform the same correction you would see from a real PHY. So essentially, you won't see anything in the trace. You don't see correctable FEC errors, and we don't flag them. So now, if there's an uncorrectable FEC error, the PHY would first try to correct it by identifying the location. If it determines that there are more than 2 symbols with errors, it would give up and send a decode failure message to the PHY. That SPL segment would be discarded, basically. Here, the analyzer does record it. It does show it. What happens next really depends on the type of traffic. An SSP packet would probably be shown as unknown with a CRC error, something like this here. If you have a primitive segment with unrecoverable errors, that would be trickier. Probably some kind of timeout or retry condition would be visible. Okay, APTA. What this does is it adds this concept of TX training on the fly. It happens in band without resetting the link, and the motivation here was to make SAS4 more adaptive to changing conditions inside the storage enclosure. So could be temperature. More likely it's bit errors detected at the PHY layer that are going to trigger this to happen. The spec, though, really doesn't define when you would initiate APTA. So that's basically vendor proprietary. It does require that all SAS4 devices support it. Only exception, optical and active cables. So it's not active with these connections. So somehow, the higher layers need to be involved because they need to basically disable APTA, based on the cable topology. Okay, this highlights a typical APTA sequence. It's different from your power-on TX training because it's done with specific binary primitives. Although, the mechanics of really what's happening under the hood is very, very similar to what happens during power-on training. This is what it looks like in a trace. It's a simulated trace made with our exerciser. So not going to look like this in the wild, but the basic sequence, there's an apta start primitive followed by apta ready handshake. Then the side that wants to improve the eye will, start requesting adjustments. And the far end needs to respond when the update is complete. There's a 1 millisecond timer that needs to be observed, before requesting the next adjustment after an update. But this is going to go on just like normal TEX training. So under what conditions will a PHY actually go into this apta mode? These are the basic rules. The link needs to be in the logical ready state, but no active connection on the PHY. That's going to be adjusted. So you have to wait for close. How long do you wait? Is there any guard band before sending apta start? None of this is defined. So there's a lot of stuff here that seems to be left to the vendor. In reading the spec, you'll also see that there's no way to knack an apta start. What they do is they're going to set some register at a higher layer that basically disables apta in real time. And this would happen automatically whenever the PHY has an open connection or is sending OOB or enters low power. All of these conditions, again, are supposed to prevent apta from starting up. And so it's basically based on the logical link state. So in theory, yeah, you would never knack an apta start. Some of the test challenges for apta, first and foremost, how do you get devices into this mode? Theoretically, you would need to degrade the signal integrity on your system somehow, right? So not easy to do. So this is where the exerciser can be useful, because you have complete control over, one side of the traffic, right? You could create a test script that walks through the apta sequence, making arbitrary coefficient requests. That way you could at least verify that the correct responses are getting sent. You may also want to verify that devices don't respond to apta requests, like during these other scenarios, like when a connection is open, during a data transfer. Here it could be, easier to use our jammer, where you would wait for one side to open a connection, then replace the open exec with a apta start, create an illegal traffic situation. A real device should ignore this, right, and reply with break, or even, it could even go to into a reset mode depending on the device itself. Okay, final point, persistent connections. These were actually introduced in SPL3, but they're getting more attention now. It's a specific feature for direct attached server storage, where you may be utilizing SAS in a more point-to-point configuration. So inside the box, the idea is that you can reduce latency by just leaving the connection open. Really, it's kind of a direct response to NVMe storage, which is connectionless. So now you could set up persistent connections, especially for flash-based storage. Hyperconverged infrastructure is another place where you could see this used. The feature requires support on both the initiator and the target side devices, right? It's an optional feature, but both sides would need to support it to utilize it. And if it's supported, it'll be reported in the identify string. Once the extend connection is enabled in the identify, both sides are supposed to start a 100 microsecond timer that basically resets every time you see an EOF delimiter, an end of frame. Now, if you're not receiving or transmitting data, they would start sending the extend connection primitive, and on expiration of that 100 microsecond timer. So basically it becomes a keep alive, and the connection basically stays open as long as the PHY is receiving a valid frame or one of these primitives, one of these extend connection primitives. How do you close a persistent connection? Either side could be directed, by a higher layer to send done normal and close the connection. There is also a 1 millisecond deadman timer running. It basically resets with every SSP frame or extend primitive. But if 1 millisecond goes by without seeing either of these events, this would cause one side or the other to close the connection as well. Okay, so assuming you have devices that support this persistent connection, you'd want to test both of these timers, right? You could start by waiting for 100 extend connection primitives, to make sure the link is in this mode, and then you could basically remove the next 10 in one direction to force the 1 millisecond timeout. You would want to see done close within 1 millisecond of that last extend primitive, so that's something you could verify in a trace. Credit starved. Flow control testing should be part of the plan, right? Because you could go hours, or even days without a close in this kind of a configuration. So a credit starved test might start by making sure you're in the extend mode and then doing multiple small block IOs. After some interval, start dropping every other R ready from the initiator side. The target, should eventually issue a done credit timeout. That would be the proper behavior. Again, the timing here would depend on the devices, but does he manage his credit buffer correctly over these longer time frames? That's the key. That's what we're testing. And again, there's a lot of other corner cases as well here. Okay, well, these are our 24 gig test platforms, which helped us create all this content. These actually were introduced over 3 years ago. So as I said, we're always on the bleeding edge with new protocols. Our work is not done, though. We continue to add features with updated software every few months. But there's lots of information on the products on our website. So, I would direct you to the Teledyne LaCroix website, if you want to learn more. Okay, well, that was pretty fast and furious. Hopefully you can watch this webinar again on demand to catch anything you missed. And I'll turn it back over to Cameron to wrap up.
Hey, thanks a lot, Mike. That was definitely a lot of material, very good material covered in a pretty short period of time. We scheduled the webinar for 45 minutes, and we're getting close to that. So we'll see if we can get to any questions. If you do have any questions, please type them in the chat box, or let's see, you can. I think there's a way that we should be able to provide an email as well. But really quickly. The 24 gig SAS ecosystem continues to grow and be ready. We're planning on production readiness in 2020. Of course, the analyzers, like those from Teledyne LaCroix, have to be there. And the rest of the ecosystem, including cables and connectors, controllers, expanders, RAID adapters, HBAs, and of course, hard drives and SSDs that can take advantage of 24 gig SAS features and capabilities. So these are all coming in 2020. And as I did mention earlier, a 24 gig SAS PlugFest is being planned for this summer. And we expect to see more and more vendors coming in. We had one earlier last year, and we're expecting to see more and more happen this year. Now let's go ahead and get to the Q&A. If you do have any questions, there is that pull-down menu or chat box that you can type it in. We did get a couple while the webinar was going on. Looks like this one here, Mike, is for you. And the question is, how do legacy 12 gig SAS storage devices connect to a 24 gig SAS fabric?
Okay. Yes. So SAS4 still uses rate matching to provide, backward compatibility for legacy speeds. So this still involves, on the upstream side of the expander, the link will still come up at the 24 gig rate. And then when transferring data upstream from a 12 gig target, the expander has got to reformat legacy 8B, 10B traffic into the new SPL formatted traffic. You're not going to see 24 gig bandwidth on that upstream link. It would need to do rate matching, right, by inserting scrambled idle, adding filler, like the align. Any deletable primitive can be used as filler during rate matching, and that's how 12 gig devices are going to interconnect with 24 gig hosts.
Okay. All right. Thanks for the answer, Mike. Here looks like another kind of testing type question for you. Are you allowed to mix primitive segments within data segments?
Okay, primitive segments. Yeah, primitive SPL segments. Well, within SSP frames, yeah, SAS4 still uses, deletable primitives, like aligns and the new link rate management binary primitive, for clock compensation. So that guy, we'll still see these with 24 gig traffic, and they can occur in the middle of an SSP frame, not an SPL segment, but an SSP frame. You can have aligns inserted, but they have to basically be inserted as a separate primitive segment or separate SPL segment. And so that is, yeah, that's still going to be supported.
Cameron?
Yes. Cameron, are you there? Okay.
Yes. Yeah, sorry. We have time for one more before I think we're going to run out of our webinar time. Is when will 24 gig SAS products be available in the market? With a more complete ecosystem and server OEM designs, we expect 24 gig SAS-based servers and deployments to be on the market probably sometime in the Q4 timeframe. And I think with that, I would just want to say thank you, Mike, and thank you to everybody who joined the webinar today. Hopefully this was helpful and had enough technical depth for those who are interested in testing 24 gig SAS. Please follow us on scuzzyta.org, visit the Teledyne LaCroix website, and please follow us on social media. Thank you very much for joining. Bye-bye.